All right, Paul. So we're going to have blocks that we want to look at that have more than one atom. So that means we're going to have to do this for n atoms. Now I'm thinking counting states when we already had 126 with two atoms is going to get a little tedious. So there must be a little mathematical trick that we can use to count our states.
And indeed there is, using probability theory. Uh, it's a classic probability problem. You may have done it in permutations and combinations at school. The situation of trying to take coloured balls out of the sack. So let's say we have the sack and it contains 5 balls and they're all numbered. And number 1 and 2 are blue and 3, 4 and 5 are orange. Now if you don't see the relevance of this to thermodynamics, hold with us.
Yes.
It will come. So how many different, let's say you bring them all, get them all out, it's a lottery or something like this, you take all the balls out of the bag and put them in a row. How many different rows are you going to get?
Okay, so let's take the first ball out.
Yep.
So there's one of 5. I got 5 balls in the bag. I got
Yep.
5 possibilities then.
Okay, and then you get the second one out.
And then I take the second ball out, but there's only 4 there now, so there's
Yep.
going to be 4 possibilities. And then 3, then 2, then 1. So I'm going to have to multiply those all together.
So it's 5 times 4 times 3 times 2 times 1. That's known as 5 factorial. So an exclamation mark afterwards indicates you're just multiplying all the integers up to there together.
Yes?
And that comes out as 120. So there's 120 different combinations you can draw out of that. But let's say we now rub the numbers off the balls. So we don't actually care whether blue ball number 1 came out first or blue ball number 2 came out. All we care was it was a blue ball.
Okay.
So we no longer care which order the red ball's in or the blue ones. We just care about how many sequences of red and blue you're going to get. So for example, 4, 2, 1, 3 and 4, 1, 2, 3 would be the same as far as we're concerned because it's just a blue ball. It doesn't matter which way around they are.
Right. So we're going to group into groups of 2 and 3. That
Yep.
is 2 blue balls, 3 red balls, and there's 5 in total. So we're going to count how many come out this way. And so we're going to have to figure out the fact that out of the 120 total permutations up here, how many combinations have the blue and the reds coming out individually.
So what we can do is we know there are 120 total possibilities, but we can divide that through by how many will look the same to us.
Yep.
So for example, we've got for each combination that are going to be, there could be one with the blue ball first and the other blue ball second, so blue 1 and 2. So we look at all the different ways we can arrange 2 balls, which is just 2 factorial. In this case,
Yep.
it's just 2, 1 times 2. And so we can divide by that. And also we've got the 3 red balls, and there are various ways we can arrange them. So it could be 3, 4, 5, or 5, 3, 4, or and so on. And we work out how many different possibilities there are way of arranging the red balls, and again divide by that, which in this case is 3 factorial, which is 3 times 2, which is 6. And so we're dividing by 2 factorial by 3 factorial, and that gives us 10.
So that's a clever little way of doing this. So how is this going to fit into our quantum states, Paul?
Well, it turns out very easily. So the idea is, let's say we want to arrange Q quanta among n oscillators. So it could be, so far we've been dealing with 4 quanta amongst 3 oscillators. So
Yep.
that's for one atom it would be 4 quanta amongst 3 oscillators. So what we can think of as being like our blue and our red balls are the quanta and the boundaries.
Okay.
So in this case you've got 3 places and you've got a boundary here and a boundary there. So if you've got n oscillators, you've got n minus 1 boundaries between them.
Yep.
So what you could do is just imagine you've got a bag containing boundaries and quanta, and you pull them out in some random order. In this case, there are 4 in the first one, so you pick out all 4 quanta first, and then we have the 2 boundaries. We've got quantum, 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 boundary, boundary.
Okay.
So that's one possibility. Let's say we had 1, 2 and 1, and now you've drawn out a quantum, boundary, quantum, quantum, boundary, quantum.
Okay.
And something like this would be quantum, quantum, boundary, boundary, quantum, quantum.
Yep.
So you're basically just taking your quantum boundaries just like red and blue balls. You don't care which boundary is where, you don't care which quantum is where, because all quanta are indistinguishable from each other. So it's exactly the same situation we just talked about, which is if you've got Q quanta and n oscillators, which means n minus 1 boundaries, the total number of microstates
Yep.
is going to be Q plus n minus 1, so that's total number of all the things you're permuting factorial,
Right.
divided by We don't care which order the quanta are in, and we don't care which order the boundaries are in, so divided by these factorials.
Okay, so it's exactly, as you said, exactly analogous to the red and blue balls. It's just that this is one collection of things we care about. That's the other collection of things we care about, and their combination, their addition to the other, is the total number of possibilities. So it's exactly analogous.
Okay, so let's see what sort of numbers we get from this. So instead of having one atom, let's have about the smallest particle you could ever manufacture, a nanoparticle with 100 atoms, which is still vastly smaller than anything we're going to deal with in the real world, by and large, unless you work on nanofabrication. So this means it's got 300 oscillators, because each atom can vibrate in each of three directions.
Yep.
So how many ways can you distribute 100 quanta of energy here?
Wow, okay. So if we just plug and chug with our formula...
So you've got 100 quanta, you've got 300 oscillators, so it's 300 minus 1 boundaries, so 299 boundaries, so you actually got 399 factorial, divided by, we don't care which order the quanta are in, so divide by 100 factorial, we don't care which order the boundaries are in, so divide by 299 factorial, and that comes out as a few by 10 to the 96.
Don't try this on your calculator at home. My calculator's not going to like taking 399 factorial.
Indeed. In fact, it's like needing a whole new system of numbers to deal with that, but you can work this out, go on to Mathematica or something like that. Well, I'm sure Wolfram Alpha can do this for you.
So there's a huge number of ways of distributing that energy amongst those atoms.
So let's ask, for example, what are the odds that all 100 quanta are in one of the atoms?
Okay.
So in this case, you can work out how many microstates one atom. So you've now got three oscillators, so 2 boundaries and 100 quanta. And there's quite a lot of ways you can arrange those. It's actually about 5 by 10 to the 5 possible ways to arrange 100 quanta in one atom.
Right.
But that's still an awful lot less than the 10 to the 96.
Yeah, so it's 500,000 chances out of 10 to the 96 possibilities.
So you're about 10 to the minus 90.
10 to the minus 90. That's like less than the number of atoms in the universe. So
drastically less.
yeah, so that is very unlikely. Not impossible, but you wouldn't want to be waiting up for it, that's for sure.
So we can apply the same thing to the situation when we have, say, 2 blocks. Let's make them different size. So one's, say, 2/3 the size of the other.
Yep.
So let's say we've got 300 oscillators here and 200 oscillators there, so about 100 atoms and about 67 atoms.
Yep.
And we've got a total of 100 quanta to distribute between these two.
Yep.
Once again, we can do the sums, and you can work out, let's say you have all 100 here and none there, 99 here, 1 there, and so on. And for each of them, you can use the equation we've just worked out to work out the total number of microstates, multiply them together. And what you find is this distribution of the number of quanta in the bigger block. And
right.
It averages out at about 2/3.
Well, it's 60 out of 60%, which
what you
is,
expect, so.
since we've done 300 out of 500, which is 60%, it does exactly what, on average, exactly what you expect. Yep. It gets 60% of the energy.
And there's some range, but for example, being down here or up there, all the energy in one or the other is 10 to the 114, in this case unlikely.
On the other hand...
Still possible. There are states where all the energy is here and here, but odds are 1 in 10 to the 114, which is not good odds.
But on the other hand, it is quite interesting that if you were going to make a precision thermometer, which effectively is a way of measuring the energy of something, you're going to want to use something bigger than 100 atoms, because you see that there is a reasonable chance to move around by even 10% in this system. So 100 atoms does jiggle around due to this quantum mechanical effect already.
But if you now go to, say, 1,000 oscillators in each, then it's starting to get very narrow.
Yes.
And then 10,000, 100,000, you're now up to the 10 to the 1,170 up there.
Right, so that's a very large number of ways, and you can imagine that 1,000 atoms, of course, is, a tiny little block. Any respectable block is going to have 10 to the, 26 or something atoms in it.
So you're talking about 10 to the 26 factorial, which I think even Wolfram Alpha would have trouble with.
Yes.
And I'm not sure how you can even write that down in any sensible notation. So in principle, you could have 2 blocks and all the heat goes into one and the other, but the odds against it are the factorial of 10 to the 23 or something like that. So do you call that, yes, there is a chance, or do you call it no? I mean, yes, there is a chance, but when the chance is that small, in some ways no is actually the more honest answer.
Yeah, I mean, I have to admit, Paul, in life, my rule of thumb is if the chances are less than being struck by lightning on a given day, then I say it just doesn't happen.
And
That's the way I do it.
And this makes being struck by lightning look like the most common thing in the universe.
Exactly.